Hey, welcome back. This is our last official day of computational mechanics, ME3255. I'm just checking our live stream settings, make sure we have audio. We've got 3255. I'm just checking our live stream set. There we go. All right. I'm in speed mode on here, but that's all right. Okay, so homework 4. It seemed like it went really well. You're getting the hang of figuring out where resources are, how to like manage Copilot help and kind of work through this stuff. Like, we're getting into the swing of things. Makes sense. We're here at the end of the course, and you probably, hopefully, learned a lot by now. I know I've seen a lot of progression, so I think you should be really proud of the progress that you've made. Like, since the first assignment till now, I've seen a lot of improvements in how you approach these and how you think about the problems. Most of you noticed that difference between like case 1 and case 2. I saw a lot of people talking about the fact that this first case is a singular set of equations, and there was one thing that came up. I wanted to show two things here. One was the thing that I thought was interesting was using this rank that people had found, and then another one was how to define matrices. I saw most people kind of manually putting them in there, but there's some neat tricks that you can use, especially if you have, this is called a banded matrix. So it has 3 kind of bands of information, a diagonal and then 2 off diagonal components. We have some tools that can actually help us build that. So let's take a look at how we can banded matrix creation. And this one's more of a trick. It's if you manually code it in there or you build it with like this kind of trick, it really doesn't matter. So if I have diagonal, and let's do this. Let's call this one a ones, np.ones of 5. So I'm going to create a vector that has 5 ones in it. And I probably need to import my, I don't have it up here. Above, import numpy as np, import matplotlib.pyplot as plt, plt.style.use 538. There. I didn't have that default in there. So first, let's just look at this. If I say diag of ones, it's going to give me a 5x5 matrix with all ones along that diagonal. Really what I want is 2s everywhere except the first and last place. So I'm going to say 2 times that. And if I wanted, I could define 1, 2, 2, 2, and a 1. But I'm not going to do that right now. I'll leave that to the end. And then what I can do is subtract a diag, this diag of ones, but put it 1. So when I give it a 1, that diag command is going to go 1 step above that diagonal. So there are 4 values here. So if I try to do it now, it's going to give me this error that I have a 6x6 and a 5x5. So really I need to say, give me all except for that last value. So now I have 2s, negative 1s, and then I'll subtract 1 more, same thing, but instead of moving it one step up, I'm going to move it 1 step down, just like this. Now, the last thing that I need to do is change that first value. So 0, 0 is 1, and then that's the last. So first value 1, 0, 0, turn that into a 1. Last value negative 1, negative 1, turn that to a 1. Then look at k again. So I bring this up because sometimes this is easier to debug than kind of manually, and easier to keep track of, because I can say like, okay, yes, this 0, 0 component and that -1, -1 component, sometimes it's easier to do it this way. Sometimes it's easier to just manually type it all in. So the other example, there's no real like banded matrix operation here in this energy balance. That one, we just have to put things down and just go for it. We just got to type out the matrix ourselves. But I wanted to show this as like a way. Okay, so then what people looked at was rank, right? Let's see, where did we get that one? Python rank. Pandas data frame. No, I want linal.matrix rank. Rank of A. Is this matrix rank? Is that what we're looking for? Maybe people imported linal import matrix rank. We could try that. And then here we can just say shape of K. Oh, and we should probably print out these two, right? All right, K is a 5 by 5 matrix. Its rank is 4. What does that mean? And here I was wondering where people had come up with this. Tell me about the rank and shape of matrices. Because I don't think I went through this. So here it's telling me a 2 by 3, so it gives number of rows then number of columns. And then matrix rank, how much information, okay, full rank, deficient rank, or if it's singular. So when you have one of the rows as a multiple of another one, and this is the same example that came up in the reading, like 1x plus 2y equals something, and then 2x plus 4y equals something else. Those are linearly dependent equations. Like if I solve one, there's not a new equation that needs to be solved for the next one. So if the rank is less than the unknowns, infinite solutions. Usually it's infinite solutions. It's not so much, and this is something that I saw come up a couple of times, and maybe AI was kind of guiding us there. It's like, oh, maybe there's no solution. Usually the problem is that there's infinite solutions. Like in this case, it's a physical problem of like we can apply force on both sides and then move it to wherever we want. So x1, if I know any value for x1, I can solve for x2, 3, 4, and 5. And that's what we do here, is the opposite. We say x5 has to be a 0, and then we can solve for the other 4. So it's not that there's no solution, it's just that there's no unique solution, that these can be anything, as long as they satisfy the physics that are still involved here. So that one, and I saw that pop up in some of the reading quiz things. That yeah, it's kind of a pedantic point, but that's why we're here. That's why we're here at UConn, is like get into the details and the mud of this. Let's see. Okay. So that was kind of a cool way of, rather than looking at the condition number and then other people looked at print np.linalg.determinant of k, and the determinant is 0, and roughly you need the inverse of the determinant to multiply times your output vector times this f0, and negative f. So if this is 0, and I'm going to say 1 over 0 times this equals x1, 2, 3, 4, 5, then I have infinity times f is x1, which is not, it's nonsensical. Like x1 is not, it could be infinity, but then all the other ones are infinity. So again, it's not that there's no solution. Usually it says there's too many. There's an infinite number, and not just multiple. Yeah, not multiple, but an infinite number of possible solutions. Okay, so 2 parts there. One was using this kind of trick to define matrices, where we can kind of do it one by one, but also set up, like, match the patterns that we already have there, and then it's a little easier to do that. Then here, so one thing that I saw coming up in this problem with like looking at temperatures in the rooms, and then also this problem of like a force balance on this truss, is this matrix did not match the actual coded matrix. And there were like different ways of kind of getting typos. I don't know if people were trying to like get AI to like trying to get the learning assistant to help them build those matrices. But if you are trying to do that, so if you identify a system of equations, so in this case, a lot of the engineering work has been done for you, where all these parameters have been defined. There's energies, and those are different from temperatures. Temperature has this conversion of like, if you know the temperature, then you know how much energy this thing has. So we've done a lot of the engineering work, turned it into an energy balance. And this comes up a lot, like thermodynamics and heat transfer. You'll end up with these kind of systems of linear equations that might be kind of hard to solve. Like dealing with 3 equations with 3 unknowns, it's not impossible, but it just takes a lot of effort. And now with AI, it gets even easier to turn this series of equations into an actual linear algebra problem. And again, I think I've mentioned this before, but if you're going to like grab things and feed it into an AI, grab the most machine readable version. So in this case, I'm grabbing the actual like LaTeX code. So I'm going to copy this whole part. So I'm going to grab like all these constants in these 3 equations. Let's make a new chat. I'm going to give it, I already have like a very specific role. This learning coach is a Python learning coach, so it's trying to teach me how to use linear algebra for coding. And now I'm going to give it a very specific task. So those are usually the 2 main things that you need for interacting with AI. One, a specific role, like, hey, you're a Python learning assistant. And then 2, a specific task. I need you to create 2 NumPy arrays, a 3x3 matrix, and a length 3 vector, so I can solve for the 3 unknown temperatures T1, T2, T3. Here are the three equations. And parameters. So again, I'm building something. It's less readable for me, but for AI, LaTeX, it has lots of LaTeX data, so it knows how to deal with that. Plugging in some numbers in here. I don't love that it plugged everything in like this. So I'm going to say use the and these might be right, but use the parameter constants in the definition of, did it call it A? Of A and B. Because I want to see how it's taking those things. I know it's taking me through step by step and saying like, hey, A11 is this, but it's kind of skipping some steps, and I don't trust AI math. It's really not very good at math. These couple of problems seem to be okay. But a lot of times, so 0.14, a lot of times it just messes up on things. These happen to be, seems to be doing the math okay. So here it's defining the constants. That's what I wanted it to do. And then I wanted this matrix, right? Like I don't want just the raw values. Okay. So now I can grab this, paste it in here. I don't need to re-import NumPy. And then I can grab this one and paste it in here. And does it create B? Yep. Oh, yeah, here's all the, oh, that's why people were doing this. This is sometimes I like to define things this way, where you define a list on one side and you set it equal to a list on the other side. Or sometimes it makes more sense. I like this version because you can have the units in the behind these, but I guess you could say pound, you could put a pound kilogram per second over here if you wanted. Okay. And B, did I grab that one? Cool. linalg.solve. Whoa, I don't need A and B. B. Then I get 15, 19, 21. So my coldest room is 16 degrees centigrade. And we could do this, 9. What do we do? We multiply it by 9/5 and add 32. No, subtract 32. How do we do? Oh, 9 over. Add 32. So 60 degrees, 65 degrees, and 70 degrees. That's reasonable based on what's our T in? So outside it's 54 degrees, inside it's 60 to 70 degrees. That's a reasonable kind of temperature where people and machines are inputting 300 watts. We're kind of moving air around through these rooms. So if you're not getting like room temperature kind of values, then there's got to be something wrong, because there's no way that we could bring in 12 degree air and somehow have the rooms be like negative 80 degrees Fahrenheit or something, or negative. Yeah, I saw that a couple of times. Cool. Then I saw a lot of cool code for this Hilbert matrix, and a lot of people used this kind of shortcut where, well, no one really used this one, but this is kind of cool. We can say Hilbert, I think it's this one. Oh, there's no Hilbert there. From scipy.linalg import Hilbert. There's a built-in Hilbert matrix in SciPy, which is kind of cool. You can define it yourself. It's not too hard, and probably the code that you use to define it is the same code that's running in the background here. Maybe they speed it up for a little bit, but kind of neat that you can grab it here. So like a 4x4, we end up with like 1/4, 1/5, 1/6, and then 1/2, 1/3, 1/3, 1/4, 1/5, 1/6, 1/7. Yeah. Okay, so if I take this linalg.condition of that Hilbert matrix, I get some value. So 1.5 times 10 to the 4. If I multiply that by my 10 to the negative 16, then it's the same thing as saying like 10 to the 4 minus 16. And that was kind of a neat trick that people had used. It's how accurate it is kind of really, if you want to get like a little closer, we could say np.finfo.eps. How do I get there? Finfo of float .eps. There we go. This is really like, if we're doing any math, this is the smallest number that we can use, that we can expect to be accurate. If it's like 1 times 10 to the negative 16, like in this case, we can't do anything with it, because if I say plus 1, I do get a number here, but if I divide it by 2, I still get a 1. There's no difference, or even 0.99 times that. Oh, that one's pretty close. 8? I don't know when it. Okay, but if we want to say, like, if we're trying to say that the accuracy is this, we could call that one our accuracy, and then do this. So now it's a little different, not much. It's still a 10 to the negative 12, because we're still taking that 4 minus 16 and end up at negative 12. And if we define things this way, now we could actually, for n in range, let's go 1 to 20 n, and we'll say let's see, how does it look? 0, 0, 0, 0, and then somewhere around here it starts shooting up, and kind of hard to see what's going on. So let's throw it on a log scale. Now we can see the expected error for each Hilbert matrix keeps increasing. And if you probably noticed that as you were going from like 1 to 5 to 10 to 15 to 20. So here's like 1 and 5, 15. Well, 15 starts getting into this like just, and even if we make this bigger, it kind of levels off. It's almost like there's two slopes, right? Like a very constant slope. And then here, once we get into this range, it's like it's slowly increasing, but mostly just noise. And what we're seeing here is that round off error that we first looked at in module 1, where we have this balance of like truncation error and round off error. In this case, we're just seeing like how round off error accumulates in linear algebra problems. But at some point, we can't even figure out what the round off error is because we can't even calculate these values. Like a 39 by 39 matrix, Hilbert matrix, the numbers are all so small that by the time we try to calculate the condition number, it just becomes large. So we're kind of limited that 10 to the 4 is as good as we can get. So I saw some people kind of build this graph, and so I wanted to share like why this thing starts leveling off. Like it doesn't just, it really would keep increasing if we had unlimited bits to actually store information. Okay, coming down. So main thing that I saw here was rewriting these pivot and LU decomposition matrices. And again, same thing, like there's already stuff that you can grab. So if you look at the reading in here, so coming down, here's like a naive Gauss elimination. So if you want to look at like a simple, so yeah, at least like as bare minimum as you can get for like solving linear algebra with Python, with computer code, Gauss naive, and then this here's like the solve. So if you have the LU, this is how to solve the solver. And then coming down, here's a naive LU decomposition. So it's saving the upper triangular matrix and then saving those factors in that lower triangular matrix. And but if you're not using like those kind of simple methods from the reading, it's usually better to just import this LU decomposition from SciPy, and there's even so it already has partial pivoting in there. So let's grab this and this one. Surprisingly, I saw more typos in turning this matrix into a NumPy array. I don't know why, but people were missing this one. Sometimes they were adding extra cosines over here. Actually, let's just try it. Let's see what if I just grab this and paste it in. Make a new chat. Maybe this is why, like whenever you try to copy it and paste it, it gets all weird. Yeah, look at this. It's all sorts of crazy, right? So again, if you're gonna use AI, then use like a computer computer savvy way of doing this. Grab the actual LaTeX equations. Much better, right? Like now I can actually see this LaTeX equation, and I think it matches. So 1 cosine 0, 0 2 sine 0, and then a 0 negative sine 1. All right, so that's what we're looking for. And then it's converting this stuff, sines and cosines. It's fine. Give me the Python code to define the left-hand side array and the right-hand side 1D array. So now I'll have oh my god, it keeps importing NumPy. Oh, the radians. That's funny. NP radians. Convert degrees to radians. I haven't seen that one. Huh, okay. That works. Usually what I see is deg to rad. And I think it's the same thing. And the nice part about that is if you're trying to go back, you can say rad to deg. And like it's easy to, at least for me, keep track of what's what. All right, so now I've got my left-hand side matrix, my right-hand side vector, run that. And if I'm trying to create that LU decomposition for this one, I can grab it from, I can either grab the stuff from the reading, which is kind of spelled out for me, and if these made sense, like if it was helping you understand the problem, then that's great. Or I can import LU and then say LU of A. And it gives me my pivot matrix, so it does partial pivoting. In this case, it's not doing any partial pivoting because this identity matrix is unchanged. It gives me the lower triangular and this upper triangular. And let's do this. Take a look at this one. So it's giving me this PLU decomposition. And there... it's not using it to solve it. So let's do a quick what function can I use from SciPy to solve the PLU decomposed matrix vector LU solve. Yeah, and so the one thing, this is a better way of doing it, but it ends up looking different. And I'll show you what I mean. So if I grab this LU factor and then say LU solve of, I think I say LU comma PIV and B, like that. And let's double check that it's the same thing. All right, so it's the same answer. So LU solve and linalg solve give me the same thing. Now, this is where our time it comes back in. I didn't ask you to time these, but I'm just showing you, like, we know how to use timers. This is where we can start asking, like, is it worth our time to go through this process? So it took 5 microseconds just using the solver. It takes 6 microseconds using LU solve. So it was slightly longer to actually dump it into this LU solver. That's not always going to be the case. I think that's the case because this is like this equation, this middle equation is we can solve for P2 without even considering P1 and P3, so it's already in a simplified form. But if we grab other equations, have I defined any other big ones? Nothing big, right? I mean, we defined this one. And I think I'm just going back up to this previous problem to see if it would make any difference here. Five microseconds and 4.5 microseconds. So here it's becoming more of a dense matrix. The denser it gets, the more, and when I say dense, I mean like there's not a lot of zeros. Like this is a 3 by 3 matrix with only 2 zeros in it. So there's only 2 out of 9 values that are 0. In this next one, we were looking at something where like 4 out of the 9 are zeros. Though the more zeros you have, the easier it is for the solver to actually solve it for you. Okay, so that's part of the reason of like why we use these LU solvers, is that the bigger these matrices get, the easier it is to store them as an LU factorization. But now let's look at, oh yeah, I gotta rerun this stuff. I didn't take my own advice and redefine, like really I should have like A2 or A3 for different problems, but I keep overwriting stuff. Yeah, and this LU gives me that, and PIV gives me this, a 0, 1, 2. So I think, what does this do, the LU factor? I know I've looked at this before, but now I'm trying to remember. It returns just one array, an n by n array, and then the pivot is telling you, it's a vector that tells you which rows were switched, rather than a full pivot matrix that we can use to like kind of factor things out. Yeah, so it definitely saves computational time to use this LU factor and then the LU solve. So if you want to try those, that's a great way to do LU factorization. It's not as straightforward as our previous LU factorization, where we had a lower matrix and we had an upper, and then even that pivot matrix, you can sort of figure out what's going on there. Yeah, so again, if you're going to like import code from other places, like rather than grabbing an LU factorizer from Stack Overflow or from ChatGPT, just grab the LU factorization from SciPy, because that one has it has a nice document. It has a nice doc string. It has a website. It has a whole like team of people supporting it. So it's a lot easier to debug and kind of go back and fix your code than trying to build everything from scratch. And again, we're engineers here. We're not like computer scientists. So even if you do write your own code, you're probably not going to make it like faster than pre-existing like imported code. Just again, kind of usual. This one people seem to get for the most part. If you were having trouble, I noticed like it might have taken like a couple of times to figure out this load text. Like you need to skip one of the rows, you need to define the delimiter, but it seemed like that one people figured out. So the one thing that I'll say, one thing that came up over and over in this last problem, like I know I didn't specifically say plot the results, but if you are claiming that you have a fit for data, you need to show that fit with your data. So import pandas, look at energy, we'll say US equals energy of energy entity. Yeah, come on. Let's look at US. So here's all my US data. We'll say T is US bracket year. E, or we'll call it like Y, I is US bracket primary energy consumption. Then let's start building out this Z matrix. I'm going to say there's a T to the 1, a T to the 0. And then this one's, I saw different ways of approaching this. This is what I think is the easiest way to do this. So let's define a split. Split equals I'll say 1984. So I'll say T minus T split, and then times T more than or equal to T split. This value, whenever you have a Boolean like this, it's either a 1 or a 0. So when this is true, it becomes a 1. So it's 1 times T minus 1984. When this is false, so if in 1970, this becomes a 0, so this whole term becomes 0. And let's look at what Z turns out to be. And I take the transpose. I use block and then take the transpose. Oh my God. Yeah, we need to close that. Open this. Close that. Open and close. There we go. So now I've got each vector. Here's my first column is the actual dates, like T. Next column, T to the 0, is all 1s. You could use np.1s like or np.1s length of T. And then this last column is 0s until the year 1985, when it's more than. I thought I said more than or equal to, right? Oh, but it's minus, yeah. More than or equal to, but it's still 1984 minus 1984. And then it starts growing until it gets up to here, so 2018. Cool. And then I saw some people use, all right, so let's leave Z like that, and then we'll say from scipy dot linalg import LST SQ of Z and YI. This one gives us more information than just saying linalg.solve z.transpose at z and z.transpose at yi, but it does give us the same constants. So there's no difference in the main output of what we're dealing with here. The main thing that comes up is that LST-SQ is also giving us, let's see, so it gives us the actual solution, which is what we're looking for. Then it gives us the residues, so B minus AX. So this one, so that 740 or 7.4 million. Anyway, then the rank, is that the rank? 3 here. And then the last one is the singular values. Is that right? Absolute value. So the rank of 3 makes sense because I'm looking for three values. And what is this one? Min of MN. P residual rank S. So the constants are P, residuals. Anyway, okay, so it gives you some more information. If you want that, it's pretty helpful. You can also calculate these things yourself. The rank is probably going to be the size of this Z transpose. So Z dot transpose at Z ends up being a 3x3, which is the rank here. And so now again, and anytime I can display these and say like, hey, this is, so what are these, like USC residual rank P, like that. 1, 2, 3, 4. All right, so there's my constants, just kind of separating out. So it's helpful. It does give us more information, but it also means we have to deal with that information. And again, so main thing, if you're making a fit, always put that fit with the data. So now plt.plot TYI, put that maybe in squares, and then plt.plot of T comma Z at USC. And now, so at least to me, the fact that I split it here doesn't really help. Like, I know I'm getting constants for everything. Like, yes, it looks like the slope is changing, but it's not. I don't think that's a good place to split the data, at least visually. If I wanted to, I could also look at the residuals and try to figure out, like, okay, what is the best place to do. So right now it's whatever, 7, 1, 2, 3, 4, 5, 6, 7, so 74 million. Now it's 59 million. It looks a little better, like it's matching more of the data here. There's more stuff going on up there, so maybe there's something else going on. But again, this, at least to me, this is the best way to check, like, is the fit doing what I think it should be doing? You gotta plot it. You gotta show something. The actual numbers don't tell you anything about that. Cool. So that was the main things that I saw for homework 4. I see project 4 is coming in, so I'll get some feedback on that. And then later on this afternoon, I'll put another video talking about some of the tips, tricks about using linear algebra for finite element analysis, and that's our last required project. And then module 5 is all bonus, so everything in this CompMech 05 boundary value problem, those are just extra credit, so it will not hurt the grade even if you try just a few parts of it and get like 10% or 50%. It's still just added points to the grade. So you're welcome to try it, or you can always go back and take another look. Like based on the skills that we've done here in linear algebra, there's going to be a lot in linear algebra, and especially this initial value problem. There's going to be a lot of stuff in this first module that makes a lot more sense now. So this is a great time to go back, try those problems again, look at the feedback, and improve the grade there. So you can improve the grade either way, either going back, redoing assignments, or trying to doing something new. Okay.